All right, up next. Okay, we talked about solutions and what a solute and solvent is and how we form a solution and the way something dissolves. And the next thing we want to talk about is the factors that affect whether something dissolves or not. I mean, if I ask you the question, if I gave you chemical X and I said, will it dissolve in water or not? Like, what's the absolute, reasons why that would dissolve or not dissolve? We would be talking about the factors that affect whether it dissolves or not. So it's going to be an important concept. So what I'm going to do is talk about those factors today. So sometimes we want to control the solubility of a solute for a variety of reasons. We want to control it. So some applications would be creating new medicines for fighting disease or even creating new compounds. So if we want to do that, can we think of anything specific? Maybe you can, maybe you cannot, but it's something to think about. All right, so number one, the temperature is something that we can do that's going to affect the solubility of something in a liquid or solid in a liquid. Okay, so increasing the temperature, what does that really do? It increases the solubility typically of solids in liquids. Okay, and that's going to be important for how much you want, whether it dissolves or not. Okay, the increasing kinetic energy allows the solvent molecules to effectively break apart the solute molecules or ions. So usually what happens is the higher the temperature, the more solute you can dissolve, and the lower the less. All right. The increased vibration or the kinetic energy of the solute molecules causes them to dissolve more readily. So when you have a solid within a liquid, you're going to be able to dissolve more at higher temperature. For example, if you have hot water or cold water, the hot water can hold more sugar than the cold water, okay, or dissolve more sugar than the cold water can because of this difference. All right. Again, this is going to be opposite for gases. Okay, for gases, we'll see that at the end of the lesson. Gases actually dissolve less at higher temperatures. All right. The nature, what the solute and solvent are, the nature of the attractive force, and what the bonding is, the nature of the solute, you can even think of the bonding here, will also be a determining factor of whether something dissolves or not. Okay, so that's important to know. So if we look at this, we would see from the previous lesson that nonpolar and polar materials don't mix, but if they have the same polarity, they will. Okay, so polar dissolves polar, don't forget, and soluble ionic compounds. Okay, again, with your molecular and ion forces. Okay, that's important for the ionic part of it. Okay, again, your dipole forces. Okay, so in this case, we talked about a dipole force in between methanol, which is, here's a methanol molecule here. Okay, and here's your water molecule. Okay, and you can see that the positive end of the water molecule attracts the negative end of the methanol molecule. And again, you'll have this situation where you have this attractive force. So again, whether something is polar or nonpolar is important to know whether it dissolves or not. Okay, and lastly, okay, for this part, as far as nature goes, is your nonpolar also would dissolve your nonpolar. So your oils, your greases, your waxes, your CH compounds will dissolve in each other because they have this nonpolar ability. So again, like I said in the last lesson, it's really important that you know your difference between your nonpolar, your polar, and ionic, because you're going to have to deal with number two fairly often when we talk about solutes and solvents. Again, solvents can only attract to, like polarities. It's important to know. All right, and lastly, we're going to look for pressure for gases only. All right, and that's going to be important to know for when you would dissolve gases. And again, a lot of times gases can dissolve or not. So when you increase the pressure, and again, we looked at pressure before. When you increase pressure, what you can do is decrease the space around the molecule. So if you put pressure on something, on a gas, you're going to force it into a smaller space. Okay. So if you have a box and you put pressure around that and force those gas molecules together, you can force them to dissolve more. We'll see that in a minute. Okay. You also can decrease the temperature. If you make it colder, you slow the gas particles down, and you allow them the more ability to attract. That will also increase the solubility of gases. So increase your pressure, increase P, and lower your T will cause the increase of the solubility of a gas. Okay? Solids and liquids are not affected by pressure, again, because there's no space, okay, in between the particles. Or if there is, it's very, very little, right? So particles. So pressure will not have an effect on the solubility or the dissolving of solids or liquids. Example, if you took, sugar and water onto the moon versus Earth, they would dissolve the same. Okay, but the pressure would be different. So you have a problem dissolving gases on the moon versus here because of the difference in the pressure. Okay, so a good example is carbonated beverages. Okay, carbonated beverages contain carbon dioxide gas dissolved under, this should say high pressure. Okay, so that's important to know. So keeping the cap, so again, under high pressure, so keeping the cap on tight maintains this pressure, okay, and keeping it cold also keeps the gas soluble. That helps keep that fizz, right? So it's important. So, a great way to remember this high pressure, low temperature thing is to think about when soda tastes best, right? Carbonated beverages are best when you keep the cap on them, right? And you also keep them cold. All right, so that's important. Cold meaning low T, right? Temp. All right, so it's important to know. All right, so a good way to see this is this little diagram. Okay, and when we look at this diagram, a good little visual on this is to look at this. This thing is called a piston. I think we looked at this in the past, but this is called a piston, and this piston can slide up or down in this cylinder. So that's a piston. This is called a cylinder. Okay, almost like the plunger we saw in class, almost like a syringe. Okay, and this can slide in this direction. So if I leave it just in this position, okay, I would have gas molecules coming out at the same time gas molecules are diving into the solution. So we're going to assume that the gas has some solubility to it. Okay, the blue area here is water, and the gas particles are actually these red dots. All right, so if you just leave this here, you will have gas molecules bouncing around in this container, and eventually they would go into the liquid at the same rate as they're coming out. So they're going in and out at the same speed, and that's called equilibrium. So you have equal rates of change here. Okay, and you have no changes, and you have a constant pressure. So we're just leaving this the way it is. Now here, if we drive the piston down, so if I put the piston down here, okay, and I increase my pressure, so I'm going to force this space to be less. You can see I'm going to now force more gas particles to go into the solution than I normally would. Okay, and if I give it enough time, I will then have an increased solubility. Okay, so now if I pressurize this and I leave it there and I give it some again, I'm going to give this a little bit of time here. I'm going to now force more of the gas molecules that were initially in this space. I'm going to force them to dissolve in the liquid. Okay, under pressure. All right, and that's going to be, so I'm going to have a new equilibrium, and this gas is going to stay dissolved. Now, of course, if I go backwards and I go back the other way towards the beginning, I can release this pressure, and I would have the gas come out. All right, and that's exactly how a soda bottle works. If you have this under pressure, okay, this would be the soda with the cap on. Okay, and if you go back to the beginning to diagram number 1 here, and I took this off, then all that gas would come out. And that's why you see bubbles form when you see carbonated beverages in that way. All right, so really important to remember for gases, okay, which requires you to know what a gas is and be able to recognize it in your formulas, okay, and to review that, increase your pressure and you decrease your temperature, okay, you will increase your solubility. Again, solids and liquids are not affected by this, and you'll have to remember that, okay?